Hello everyone, and welcome to our final video on graptolites, where we're going to look at how they are useful to us as geologists, and also what they look like within a rock. So let's make a start. So graptolites, as I've already mentioned, are commonly found in sediments. Sometimes even these sediments are called graptolite shales, but they're examples of often anoxic black shales, low oxygen, lots of carbon in them. These generally represent lower shelf margin to deep, always low oxygen environments of deposition. In these environments, there are very few things to destroy fossils, and so when we find our graptolites, there are often quite a lot of them. They occur in abundance. This slide shows some typical examples of graptolites in a rock. You often find them as carbonized films on bedding surfaces, such as all of these examples here. They were not very stiff, these colony housing structures, and so they flatten very easily, and thus they are each bedding plane can be packed full of examples of flat graptolites. And they also, I should note, rot fairly easily, not the housing, but the zooids themselves. So in terms of the zooids, the actual individuals, those are pretty much unheard of in the fossil record. So when we're talking about graptolites, we're only talking about this tubarium, which survives because it's a bit tough, so it has a higher preservation potential, we would say. While shales are by far the most common rock in which graptolites are found, they also occasionally occur in other marine sediments. Known examples include sandstones, mudstones, and limestones. So typical are shales, occasionally other rock types. Very occasionally we also see them in volcanic ash beds. But also note that these creatures may have floated and thus been transported for significant distances prior to their burial. So that complicates slightly what we can say about them. An interesting thing that we can see in some deposits is that specimens can become aligned by ocean currents. So for us as geologists, these could be very valuable paleocurrent direction indicators. The left-hand side example here is one from Ayrshire in Scotland, and you can see that all of the graptolites are aligned within this rock. More frequently though, I wanted to highlight these creatures are randomly orientated, as shown in this example from Germany in the Lower Devonian. So that's typical. This is unusual but useful. Bear in mind also that these anoxic black shales can become strongly weathered once they're exposed. They don't like being at the surface. And in this case, even though they're called black shales, they can appear quite light in colour. And I've put some examples of these on the right. These are examples from the Ordovician of China. And the remains of the animals on these are generally seen as small carbon flakes. Note that because these are flattened and concentrated onto our bedding planes, they don't really appear in slides that often, unless you make your slides exactly aligned with the bedding plane, and then they just look like they do in hand specimen. Hence for this lecture, I don't actually have an image showing what these things look like in slides. So sorry about that, but that's because it doesn't look that different to what they look like in the rock themselves. So we'll finish by highlighting why these creatures are useful to us as geologists. I'm sure you've guessed answer number one, because a pattern is forming here. Many of the fossils that we've covered in this course, we've covered because they will be useful to you as a working geologist, and that's because they're really useful for biostratigraphy. The graptolites in particular are so prevalent that they are of key importance in correlating lower Paleozoic strata. So they are our top-notch lower Paleozoic biostrat fossil. Traditionally, 4 sequential graptolite faunas, or kind of like groupings, have been recognised through from the early Ordovician to the early Devonian. As a more specific example, key Ordovician and Silurian biozones are generally based on graptolite species or assemblages of graptolite species. So you can see some examples of Ordovician and then Silurian zones on the left-hand side of this slide here. Remember that to be a good zone fossil, you need to ideally be widespread, facies independent, evolve quickly, easily recognised, and have a good preservation potential. And this is true of the Graptolites to differing degrees, but these are generally really good zone fossils, especially for the early Paleozoic. I guess the only bit, as we'll discover in my next couple of slides, that they are not so good on is that they're not always globally distributed, so they're not as widespread as we may like. Graptolite correlation charts show that the biozones based on Graptolites vary from about 0.3 to about 2.4 million years in duration. So that's really quite a short time, especially when we're looking 400 million years into the past. So that's pretty good. Whilst some Graptolite zones are worldwide in occurrence, as I just mentioned, many work best at a regional scale because they are not as widespread as we would like. On the right here, you can actually see an example of a composite section. So this is what we learned about in the last Zoom session. And this is based on all of the available evidence from 14 sections worldwide from the lower to middle Ordovician. So this is a way of taking all of our Graptolite fossils and trying to understand what's going on in the sequence in any given area. So we've got on our bottom, on our x-axis, the composite standard sequence here, and on the y-axis we've got the Australasian sequence here. So we can actually see changes in the gradient of this line that indicate changes in sedimentation rate, for example, in the Australasian sediments. So that's really, really useful. And this is this is a piece of ongoing research that has been updated in further studies after this one to include nearly 2,100 appearances of individual Graptolite taxa. So this is a really good example of a group which lends itself towards graphical correlation. So it does exist in the real world. It's being used in research at the moment to understand diversity changes and to develop ideas on evolutionary patterns like extinction and origination events. So yes, Graptolites useful for biostrat, but they're useful in a couple of other ways as well. So we can see patterns in water depth in terms of the Graptolites that we discover too. So we often find that faunas from shallow water sediments are lower in diversity or may even be monospecific in terms of their species makeup, so only have one species in there, whereas deeper water faunas tend to be highly diverse when it comes to our Graptolites. Not only does this help us get an idea of water depth, but it helps us identify as geologists transgressive sequences in the rock record, so changes in sea level. That's an incredibly useful thing to be able to say. We've got a nice example in this diagram here, which is it shows how we can differentiate in inshore assemblages. This is the Dinimagraptoid biofacies in its technical term within this context. And this facies is characterized by the presence of an assemblage of entirely endemic, so local faunal elements. These are things that you'll only really see in one particular area. As we get towards deeper rocks, we enter a shallow epipelagic biofacies. So that's around here, which is an assemblage that includes both cosmopolitan faunal elements, so those which are globally distributed, but also some of our endemic taxa, so those are some of the local ones. So that's as we're getting towards deeper waters. And as we transition further into deeper, so mesopelagic biofacies, you can see these depths actually marked on the diagram here, we start seeing widespread taxa. These are the things that are called pandemic fauna in this diagram, which I didn't think was particularly useful because given its different use of the word pandemic to the one that we're used to at the moment, but there it is on the diagram, so I should mention it. And this is our isograptid biofacies. So bear in mind that we have this pattern of local fauna, so no good for global biostratigraphy, those ones, but probably very good for local biostratigraphy in shallowest waters, getting towards more cosmopolitan taxa as we get towards deeper waters. Okay, and then take that and bear in mind that because you have this local fauna here, that's all overprinted by biogeography. So the Graptolites have been very useful in studies of Ordovician and Silurian paleobiogeography. And this requires a really nuanced analysis because what we're looking at here is trying to differentiate all of these patterns of evolution from environment from region. But the latest research shows that this is possible. So we can resolve assemblages based on their oceanographic setting, their water temperature, and other factors. And this means, as a result, that we have distinct latitudinal and depth differentiation of graptolite faunas. And those have been established especially for the lower to middle Ordovician period. This not only suggests that we have a considerable influence of oceanographic and climatic controls on our graptolite distributions, but it allows us to identify lateral variations of graptolite fauna along depth or temperature gradients in large ocean basins. That may make it difficult to correlate fauna across one of these oceans, and different local biozonations may be used, but it can be very useful to help us understand the paleobiogeography of given rock units. So a really good example of this is that we have different assemblages from the two sides of the Paleozoic Iapetus Ocean. So you can see this ocean here with Laurentia on one side and Baltica on the other. So this is these are continents that eventually collided during a mountain building event. But based on the different assemblages of graptolites that we have in the rocks, we can build up a picture of where any individual rock formation was, both in terms of its water depth and in terms of its latitude, and i.e. which continent it was on. So we can identify, for example, both a shallow water and an oceanic biofacies for both of those continents, allowing us to unravel both depth and paleogeography. So that is another way in which graptolites are super interesting, and that brings me to the end of this video, and also to the end of the videos which are looking at particular animal groups, I'm afraid. I hope they've been interesting and enjoyable, but in our next set of videos, and the final set of videos for this course from me, we'll be looking at a couple of other groups that I haven't included, but you should still know that they exist and what they are. And then we'll be looking at, very briefly, supported by the Zoom session, how we can use fossils to identify the environment of deposition of a rock and some of the things that we should consider when doing so. So with that, that's it for graptolites, and that's it from me for this video, and I will see you sometime soon. Take care.